It's a great pleasure to have you here, Janet. Janet works in quantum thermodynamics for a long time, so it's a great specialist in this field. And thank you very much for accepting our invitation, Janet. You have 40, 50 minutes. And do you mind if people interrupt you in the middle to make questions?
No, that's great. I like it when people.
Okay. Yeah. And people following YouTube, just if you have questions, just type on the chat, and I will transmit the question to Professor Janet. And Janet, thank you very much. The screen is yours.
Okay, thank you very much, Lucas. This is really nice to be here and give a talk. And I haven't given an online talk for a while, and today I have a bit of a cold, so I might be a bit quiet at times, and hopefully it's going to be okay. So thanks very much for inviting me. I'm going to talk about some work that I did with quite a few people who are here. And the talk will be about quantum signatures in stochastic thermodynamics. So here is a brief slide with some of the papers and some of the people involved. So some of the work started with Philip Kammerlander in 2016, and then this was sort of topped up by work with Hamed Mohammadi and Alexei Ofev. And then at the very end, I'll talk about some other aspects that have to do with stochastic thermodynamics in the quantum regime. That was done by Harry Miller and Matteo Scandi together with Marty Perno here. Yeah, so here's an outline. I'm not sure who exactly is in the audience, so I will very briefly start with a historical overview to put this into some context. And then I will talk about these things, so work from quantum coherence in the optimal case, and then what happens when it's not optimal and irreversibility starts to happen. And then we'll talk about these things, that there will be two types of being out of equilibrium and entropy production arising from it, and so on. And towards the end of the talk, I might start the second topic, depending on time, which is about the fluctuation dissipation relation in the quantum regime, which has quantum signatures, so it's different from the classical one. Okay, so let me start with the historical overview first. So that's sort of my starting slide for many of the talks to remind people that thermodynamics, of course, is a relatively old theory, and we have the laws of thermodynamics. They talk about entropy and all that. And then people also know that there's something called information theory, where there's another entropy, of course. And a lot of the work we do in quantum thermodynamics sort of connects these two types of theories. And one of the key central ideas about it is really Landauer's principle and the identification that information is physical and that the two entropies can somehow be related in some sense, not always. Then one has to be a bit careful. And one of the main things that Landauer basically talked about was this erasure process, which is a state transfer from an initial state, which is one bit of information. So either we have 0 or 1 with probability 1/2. And the state transfer is, okay, let's take this one bit of information and make it into a blank state. And the question that he was discussing was, is there any heat or work associated with it? And what he showed was, indeed, there is a heat, for example, associated with it. One generates an amount of heat in such a process that is at least kBT log 2. And T here is the temperature of the environment in which such erasure process would happen. So that's all relatively well known. This is just for people to be very reminded of it. So now people, of course, know that out of information theory, quantum information theory was later developed, actually in part because of Landauer's insight that information is physical. And at the same time, statistical physics, which of course is a microscopic description of macroscopic thermodynamics, also was sort of got an upgrade in a way, and that's called stochastic thermodynamics. I'll very briefly talk about this in a moment. Namely, what is stochastic thermodynamics about? It's about things, for example, like this Dzerzhinsky equality, which makes a statement about this here is an averaged work, but it's exponentiated. So what you have to imagine is you do a process such as a pooling of such an RNA molecule, and you do this many times. And because it's a very, very small system, every time you do it, you will get a different work. So these are the type of traces you find. And if you then take the exponentiated value of that work and average it over all these experiments, then the promise is that you will get this equality, which is e to the minus beta delta F. So delta F is the free energy difference of the two endpoints. So the free energy of the initial unstretched one and the final one, which is very stretched. And so what's amazing about it is that this really is a highly non-equilibrium process on this side, where the stretching happens is very non-equilibrium. And it could be very slowly done, or it could be really fast done. So it can be highly non-equilibrium. And on the other side, on this side, one has a quantity that is very equilibrium. It only depends on the endpoints. And the promise is that it's always equal. And that's very, very powerful. So this is the Straczynski equality. And the notion of associating thermodynamic quantities such as work with trajectories like this, that's what stochastic thermodynamics is about. Right, this is classical stochastic thermodynamics, and so my talk is really in quantum thermodynamics, and as a field, quantum thermodynamics sits somewhere between this sort of quantum information theory branch and also the thermodynamic and stochastic thermodynamics branch, and sort of connects these ideas. So for example, there's something called resource theory, which comes from quantum information theory and talks about aspects of quantum thermodynamics. I'm not going to talk about this today. And then there's also something called quantum fluctuation relations. So they are the same thing as this one, the classical Straczynski, but then extended to the quantum regime, right? And so including quantum effects. And yes, so one of the points here is that when one does the quantum Straczynski equality, I'm not going to go through it, but basically that would be the slide with all the explanation of how you go through it. You can read this in these papers. What you eventually find is that you actually get the same prediction as classically. So you get the same relationship for a quantum system undergoing this type of process, this non-equilibrium process, and the relationship is still this equals this. So in that sense, it was a bit back then when this was still not knowing what I'm going to talk about next. There was a real sort of puzzlement about, okay, there seems to be no quantum feature. There seems to be nothing particularly exciting quantum when one goes from the classical stochastic thermodynamics side to the quantum side. So can we come up with something that is quantum, really quantum? That was the question we asked. And yes, there is of course an answer, and eventually it's going to be very easy once you understand it. So the answer is, okay, let's take Landauer's reset process, this one, and make it somehow more quantum, because this is actually classical. You can erase one bit of information classically as well, and you get this. In fact, that was what Landau was talking about. So how to make it quantum? We can do it like this. So consider some initial state rho, and we're going to map it to some state eta. And eta is a state where basically we've just taken some projectors, and you can imagine these projectors being the projectors onto the energy eigenstates of some Hamiltonian. And we take these projectors and project our state on these eigenstates, and then you get eta. So if you think, for example, of a qubit, here's a sort of blob sphere. You have your energy axis is the pole axis from the North Pole to the South Pole, and our initial state rho, for example, lies like this. And then this projection process that leads to eta is the one where you basically project this Bloch vector into the energy basis. So the red vector is the result. And the point is that, here's an example. So if you had, for example, a superposition state of two energetic eigenstates, then your density matrix would look like this. And what we are talking about is that you eventually get this eta state, and the eta state would simply be a mixture of these two energy states. So we would have the same diagonal, but the off diagonals will have vanished in the energy basis. So that's the mathematical statement of this picture here. So we're going to look at such a process from rho to eta. And what we showed in this paper, which is now a few years old, is that one can extract work from such a process. And this can be done whenever there were coherences in the initial state. So the work that one can extract is at most kBt times the entropy difference, and this is the initial entropy of rho, and this is the final entropy of eta. And this is always a strictly positive difference when the initial state rho has coherences. And what do I mean by coherence? Of course, I mean that this state here is not already diagonal in the energy basis. So whenever it has coherences, one can at most get such an amount of work out. Okay.
Janet,
yes.
Just a question. Is this under a restricted set of transformations or under any unitary transformation?
This is set up in, and I'm going to go through it a bit more.
Ah, okay.
Yeah, so I mean, this is, of course, it's not unitary because it's actually in, you are allowed to connect it to a bath, and the bath has temperature T. So you can't change, of course, the entropy of your state by just doing unitaries, right?
No. I'm talking about the extraction, the process of extraction work from the system.
Yes. Yeah, okay, let me continue. I think I understand the question. I think I'm going to answer it more. So just to say, so this is the extracted work, and what we showed in the paper under situations where you can connect your system to a single bath at temperature T, or you can do unitaries as well, then you get this bound. And so the optimum is achievable. So we construct a protocol in which you can achieve the optimum. Of course, it's a theory protocol, right? Doing it experimentally is a whole different thing, but it is an achievable bound. And some questions that I will talk about today more is that fundamentally, actually, I've put these sort of average signs around it, but what is it actually an average over? We didn't do that in this paper. Here we used very simple arguments to argue for this bound, but we now have some more information on this. And also, how does irreversibility affect the work extraction? So how does this work? So basically, so to straight away talk about irreversibility before we continue, when does irreversibility occur in any process, thermodynamic process? It occurs whenever a non-thermal system is brought in contact with a bath at temperature T, right? So for example, think of a classical system that has some populations that are not of Boltzmann type. You bring it into a contact with a thermal bath when you get jumps from the different, say, energies into other energies to make the probabilities be of Boltzmann form. And so that is an irreversible process. And the associated quantity with such irreversibility is the irreversible entropy production as irreversible. And what we know from thermodynamics is the following. So the total heat dissipation, that would be the Clausius statement, is you can write it like this, and this is my sign convention. So the dissipated heat is minus just a Q with no labels. And the dissipated heat then is minus T delta S. S is the entropy change in a thermodynamic sense. And then when you have irreversibility, you get a surplus of dissipated heat. Okay. So when you do some process, you start with some initial state, you go to a final state. When you do it very, very slowly, the dissipated heat is exactly this difference, minus T delta S, with delta S being the difference of entropies. If you do it fast, you will generate a surplus of dissipated heat. Okay, that's because the process becomes irreversible. And then for work, there's a similar relationship. So here's the extracted work. In such a process, you might extract work into some work storage device. And the work extraction is in the quasi-static limit would be minus delta F, which is simply the free energy difference of the system after minus before the process. And if you don't do it quasi-statically, so you do it in a way that irreversibility occurs, then you get a reduction of your extracted work or non-recoverable work that you lose by this irreversibility. So I refer to these two things as the footprints, the energetic footprints of classical irreversibility. These are the two things where you can see irreversibility. And one of the questions we have here is, Are the energetic footprints of irreversibility, are they the same in the quantum regime? You see, are they the same in the quantum regime? It's not so obvious whether that is true. Okay, so let's go through the protocol of doing this work extraction from quantum coherence, firstly in the optimal case. So again, just to remind you, the aim is to remove coherences, but now in a controlled process to extract the work. So we go from rho to eta with some heat bath at temperature T and some work storage system. So in our system might be some qubit, for example, with two energetic levels, E1 and E minus and E plus. And now we do a process on them to extract this amount of work. And the best way to explain it is probably more graphically. I'll show the equations in a minute, but they take forever to process. So, so let's just go graphically. So we have initial state rho is over here. It might not be pure, right? So it can be inside the Bloch sphere. And we want to move it to eta, which is over here. So this is the one that is diagonal in the energy basis. And what we're going to do is we're going to move it first this way, and we can do that by unitary evolution. And then we want to do this, this transformation, which cannot be done unitarily. And here's the sort of list of all the things one has to do. So firstly, yeah, as I said, we evolve the state unitarily. And we also quench the Hamiltonian. We quench the Hamiltonian such actually that the qubit becomes at the end of this process of the green process, it becomes the thermal state. So this can always be achieved. One can always change the energetic level such that whatever the population is that this state has, the population of this is fixed because this is the same population as we originally had, just transferred into a different basis. So the populations are fixed. And the temperature is also fixed because I'm thinking of my environment having a fixed temperature. But what we can change is the Hamiltonian splitting of the qubit itself. And by doing so, we can make this state to be actually thermal by its populations. Okay, so we've done the green process and we are here and we're actually now in a thermal state, which is slightly weird. But at this point, we can now couple the qubit to the bath. So until here, we've actually assumed our qubit evolves unitarily without interacting with the bath in the ideal case. And at this point, we're here, we are connecting it to the bath now, but nothing happens because the system is already in a thermal state. So it's already in equilibrium with this bath. And after that, one can quasi-statically change the Hamiltonian. As I said, we are allowed to change the Hamiltonian energetic splitting of the Hamiltonian. We can very slowly change that such that the system, while the system is in contact with the bath, and what this does is it realizes a quasi-static process where the system slowly changes its own equilibrium state at all times to move over to where we want it. That's how we do it. We choose our Hamiltonian such that the final state is this. So what I've outlined now is a process that brings us from there to there by thermodynamic steps. And yeah, so if one goes through all of this calculation that's in one of the papers, the 2016 paper, then you find indeed that the work extraction that I promised you will be achieved. So I'm not going to show the formula again, but it will be achieved. Today, I want to focus on what happens if you don't do the perfect protocol. So if you don't do the perfect protocol, this is the point where irreversibility can come in. So that's the point, at the point where we couple our system to the bath here, if we haven't got it in the perfect thermal state, this is the point where irreversibility will occur. And we can draw this like this. So for example, instead of doing the perfect unitary, we do one that's slightly too short. And instead of doing the quench of the Hamiltonian just correctly, we do it such that it isn't exactly the tau state, even by populations wise. So what we then have is that the state after this second step is over here still has some coherences. So we've removed some coherences in a good way, in a unitary way. But now we are going to connect this state that still has coherences to our thermal bath, and irreversibility occurs because our system is not in a thermal state. And So what we're going to talk about now is that actually there are two types of being in non-equilibrium and two types of entropy production that arise from that. And it's very easy to see. So from this point to that point, actually the point is that one can sort of take this apart into two bits, namely this is the coherence part, the quantum part, and this red bit, which is the population part. It's the whether the populations are correctly thermal or not. And so just again, so this blue part is coherence before contact with the bath, and the red part is non-thermality before contact with the bath. And if one thinks about trajectories, so these are trajectories, our system, you can think of this state rho tilde as being, of course, a mixture of either this theta tilde and theta, these two states, and then they go over into. So our initial states are theta plus, or theta minus, and we will go to E plus or E minus in a trajectory picture. But we are going to decompose these type of trajectories now. So the full thermalization trajectories can be decomposed into a decoherence part, which we call this funny stuff, and then a classical thermalization trajectory part, which is the red stuff. And in pictures, it looks like this. So we can go, basically it's this blue stuff and this red stuff, but on the basis of trajectories. And the reason why it makes sense to introduce such trajectories is because then one can also talk about entropy production. So entropy production as a stochastic entropy production is defined like this. So this is a general formula for the entropy production. It says that the probability of going forward along some trajectory has to be divided by the probability of going backwards, this type of trajectory, and then you take the logarithm. So obviously, if you get the same probabilities, then this ratio is 1 and the logarithm is 0, so there's no irreversibility. So in other words, going forwards and going backwards is sort of the same, then this becomes 0. If the probability is biased, there's a more likely scenario to go forward than backwards, then this irreversible and an entropy production will be non-zero. And so now we have constructed our trajectories here, the blue ones, which are the decoherence ones, and then the red ones, which are just the classical thermalization trajectories. So what we can now do is we can split the stochastic entropy production into two parts, a quantum and a classical part. So here we just take this formula, and we're going to look at the trajectories for the quantum part and the classical part, and it does split. Mathematically, it splits as well, you know. And now we can look at these two parts. So here's the quantum part for the irreversible entropy production, which is just defined like this. You take it for each trajectory, and then you average it with the probability of one of those trajectories happening. That's the P. And the same for the classical case. So classical entropy production for one particular trajectory times the probability for this trajectory to happen gives you the average classical entropy production. Right. And then one can calculate what that is. And what one gets is this is simply what is known as the Kullback-Leibler distance. So each of those average entropy productions becomes just a geometric quantum Kullback-Leibler distance. And if we look into the picture, it looks like this. So here is rho tilde, basically. This is our initial state. And then, where's my eta? Sorry, I haven't got the eta state. This eta state is the one that would be projected over here. So that would be over here. And then this eta tilde state to tau 1 is this step. So it simply in this picture here, it simply is the distance between these two guys plus the distance between these two guys, geometrically speaking as well. So the totally irreversible entropy production is consisting of these two distances, which then come together to one distance. Right. Good. So now that we have two irreversible entropy productions, we're interested in the footprints of this irreversibility on the energetics. So the energetics being the heat and the work. So first we're going to look at heat. So classically, you know what heat is, of course. You know that heat is, of course, the exchange of energy with the bath. And what does the bath do? The bath makes you jump from, say, the excited state to the ground state, or from the ground state to the excited state. This is sort of this continuous exchange of energy with the bath makes you jump this way. And the energy in each such trajectory is simply the difference between, well, N and M are simply numbering the levels here. N is that level and M is this level. And depending on which jump you do, you get 4 different combinations. You get 4 different values of the heat that is exchanged with the bath. Now, there's also something called the quantum heat. So this was first introduced by these guys here, Eloi and these other people, including Alexia Hofer. And so the stochastic quantum heat is very analogous to this one. It's just a little more complicated because actually the initial state of our qubit isn't in an energy eigenstate, right? This theta state here is something that is, remember in this picture, is something that is either here or there. So these are not energy eigenstates, but we still want to associate an energy with it, and the way to do that, of course, is to take an expectation value of the Hamiltonian in this state. And then the heat is simply also, again, the difference in the energy that is experienced by the system when it is exchanging energy with the bath. Okay, so we have 2 definitions of heat, the classical one and the quantum one, and this is done on the basis of the trajectories, which are these jump arrows here. Now I want to plot them. So here are the different arrows. Let's start with the red ones. Yeah, let's start with the red ones. So the value, so Q is shown here. Q is the value of the heat. So either we jump up, then, okay, now I've forgotten my sign convention. Let's say it's this red one. Either we jump up, then it would be this value 1 in terms of h bar omega 1, which is the splitting of the qubit. So if we jump up, this is the value of the energy exchanged. If we jump down, it would be this value -1, right? Either up or down. And what we see here is that there's an imbalance of the probability of jumping up or down. So this is the classical heat distribution. It is more likely, say, to jump down than to jump up, for example. This is the imbalance here. And then there's also transfers that have 0 heat. These are the ones where plus goes to plus and minus goes to minus. And the probability of that is actually the highest. Okay. Now, here's the quantum heat shown more. These are different situations. So the first one was when the state rho theta has classical non-thermality. Remember, I should have put that down. Remember, the first scenario that I was just talking about was if the state before contact with the heat bath has only classical non-thermality, so no coherence, so no blue part, just the classical non-thermality. So only the populations are out of sync, only they are out of equilibrium. And that was the first picture, sorry, going forwards. That was the first picture that I showed you here. Then we only have classical heat, and it looks like this. Now, if we have quantum coherence instead, so classically there's no problem, but we have quantum coherence and we connect our system to the bath, we get quantum heat, which is the blue things here, and we will get 4 different values with 4 different probabilities. And it's now 4 different values because we have 4 different arrows, and each of those states has a different energy. So the transfers are always different. And this is just an example of the different probabilities that you can get for a specific example here. Okay, this is all a bit much. so please ask questions if that doesn't make sense, because it probably doesn't make sense. So let me continue though, if there's no questions. So what one can now calculate on the basis of the definitions of the heats that I've given you, and the basis of the probability distributions of the heats that I've shown you on an example here, one can then calculate the average heat, right? So the average classical heat would be this symbol here, Q classical, and the average symbol. So this is averaged over all possible trajectories. These are all the red arrows here. And what one then gets is this, after some mathematical manipulation, one gets this. So this here is simply the entropy difference again, of the end state of the classical part and the initial state, or the other way around. And here is the average irreversible entropy production. And what is now the thing that you should recognize is that this is exactly the formula I showed you earlier. This is the footprint of irreversibility for the classical heat. So that's the Clausius expression. If we do the same thing quantumly, what you find is that the average quantum heat is 0 in this setup. The average quantum heat is trivial, it's 0. While the irreversible entropy production for the quantum part is non-trivial. Okay, so it's the difference between these two entropies. And so what this sort of implies is that the standard heat footprint, the one that connects the heat with the irreversible entropy production, that one is not true for the quantum equivalent. There's a broken link here. This one is 0, this one is non-zero. That's it.
But what does this mean actually, Janet? Because I mean, yes, we expect the heat to be linked with the entropy in some sense. And okay, the classical part is fine. I mean, the physical content of the thing is there, but the quantum regime I didn't get.
Yeah, no, it takes quite a while to understand, or partially understand it. I mean that the average quantum heat is 0. Is sort of comes because the process that we're looking at is one where really all that happens is that we have this transfer of, it's this part, right? We have our initial state that has coherences, and we simply connect it to a bath. And in this process, the energy change that the system experiences on average, of course, is 0, right? The initial state and the final state, they have the same energy as a full state. And everything that happened during this process is that it was connected to a bath. There was no work in this part. So the average quantum heat that was exchanged must be 0, therefore. So this part is actually trivial, that it's 0. But the irreversibility on the trajectory level is not 0, because you are not going to go back. It's quite obvious that you won't be generating coherences. So you know, there's a real tendency, of course, of losing coherences. So the irreversible entropy production is non-zero, simply speaking. And that is different from the classical regime. In the classical regime, you have a link between the two. And in the quantum regime, in the setup that I've been discussing, this is 0 and this is non-zero. And there's no such equality between the two of them.
Okay. Yeah. No, I have to think a little bit more.
Yes. It's not very easy to understand it all. One has to think about it quite differently from the classical case. Let me continue a bit more.
Okay.
So there's also a work part. So work, sorry, there should be no end, work footprint of irreversibility. So to sort of discuss this work footprint, it's useful to look at the entire protocol again. So what do I mean with entire? I mean, we take the initial state, we want to go there, we do all this, we just make a mistake at this point where instead of going perfectly, and getting what I promised at the very beginning. At this point, we have not the perfect state. We connect to the bath and we get these two irreversibilities, the quantum one and the classical one. And we want to now know how much work do we lose because of these irreversibilities occurring, right? So the full protocol, the extracted work is the entire change of energy plus Q, the average Q. And what is the entire change of the energy? It is the energy of this state compared to the energy of this state, but this is zero. There is no change of energy. So again, the entire work for the entire process is just the change of, is just Q, the heat exchange. And now what heat exchange is that? Well, we have different parts of heat exchange. We have firstly the blue part, which is the coherence loss here, which is a coherence loss that is only occurring because we're coupling our system to the bath. Then we have this red part. This is the standard classical heat that occurs when we connect our system to the bath while it was not in equilibrium. And then the last bit is this orange bit, which is the quasi-static change that we're still doing. During that change, we also exchanged heat. So in trajectory arrows, it looks like this. So we have different types of possibilities of transfer. And then one can work out what each of those bits are. Yeah, so basically I've done it all, of course, and it's in this paper. And what comes out in the end is the following. One gets the full protocol gives you minus delta F for the full protocol, minus and then T times the two irreversible entropy productions averages, right? So here this is the classical irreversible entropy production and this is the quantum irreversible entropy production. And so what that means is that this is exactly, the work footprint is exactly the same in the quantum and the classical regime. That's what we were expecting. We were expecting the work extraction to be minus delta F when everything is perfect. And when irreversibility hits, we want this to be the entropy production that reduces our work. And here we have now two contributions, classical and quantum. Yeah, so we get both such reductions. And one can plot this as a figure in terms of the coherence. That's the coherence before contact with the bath and non-thermality before contact with the bath. And if both of them initially are zero, so that's this point here where both of them are zero, that would be the maximum work that we can extract. So that's the best. And then if you have coherence beforehand, you will go down this route. And if you have non-thermality, you will go down this route. And you have a little bit of both, you will go down somewhere diagonally. And so what you see is that, you know, there's a certain regime, of course, where you can extract work from this entire process, but very quickly, when you are not doing it perfectly and you make an error here, you will reduce this work extraction quite quickly, and you actually have to pay. You have to pay work to do the process. Okay, so yeah, the summary of all of this is, what's my time? Yes, I still have like 5 minutes or something.
Oh, you're not strict in the time. I mean, you can simply talk.
Yeah, okay. No, I don't want to overdo it. I mean, I'm at the summary here. So the summary is, we've talked about a quantum system and how it can be out of equilibrium in two ways. It can possess energetic coherences and it can possess non-thermal diagonal entries, classically non-thermal. So that's the blue and the red bit. And what we found is that contact with the thermal bath results in two irreversible entropy productions. We have the quantum part, that's the decoherence part, and we have a classical thermalization part, that's sort of the standard part. And then we looked at distributions of heat. So for example, we have classical heat and quantum heat that were distributed in such a pattern. Of course, that depends on the initial state that we were looking at. Everything depends on very many details. But in general, one can always write down such a probability distribution for the two heats. And what we showed is that the average heat, quantum heat, and the average quantum, the average irreversible quantum entropy production are not connected anymore as they used to be for the classical case. And then we looked at work, and we saw that the maximum gets sort of depleted by the irreversibility in a very similar way. The classical and the quantum way both reduce the maximum work. Yeah, so we had the occurrence of a quantum heat, and we had a reduction of this extracted work with the two entropy productions. So to say it another way, because it's really confusing, and hopefully, Lucas, this is the point where we can talk again. There are two ways of removing coherence. What I talked about first is actually the reversible removal of coherence. This is when you do the full green thing and then the orange thing perfectly. You have no irreversibility, and your entire process gives you work. You can generate, you can extract work from the coherences. That's the reversible removal. This is a quasi-static process throughout. And then we have the other side, which is the irreversible removal of coherence. So this happens when you have this state and you connect it with a thermal bath, and it irreversibly removes these coherences. And when that happens, you get a non-trivial quantum heat distribution. That's the blue dots here. And so what one has is the interplay of these two ways of removing coherences. And you can get work out of it, or you can have a non-trivial quantum heat distribution. Okay, so that actually wraps up this part. And I'm going to spend like 3 minutes or so, or 5 minutes on the second part, which is very interesting, but it's also quite different.
Just one question before you continue, Janet. So apparently heat is deeply linked with coherences. With change in coherences, actually, not coherence, but changes in coherence. So is it possible to change the definition of heat, and because there are papers by old papers now, 2011, 2012, something like this, by Pokovinikov and some other guys, where they actually define the heat in terms of coherences. So what happens if I just define a heat in terms of coherence? What's going to be changed here? Apparently, the average heat, the quantum heat, would not be zero in this case, because coherence is being lost there.
Yeah, I'm not. I can't tell. I can't tell. I mean, obviously, if you change the definitions of what heat is, then it would change everything. The heat definition we used here was this quantum heat definition by Eluard and so on, and Alexei. I know there are many different papers and many different definitions, and depending on what one chooses, one of course gets a different sort of prediction in the sense of it then eventually will depend on how you measure something and what you assign to be the heat contribution, what you assign to be the work contribution, right? So I can't tell you what would happen for a different definition, but it's a good question to think about it.
Yeah, because your expressions are I mean, they like a reversible entropy. Your expression for irreversible entropy, it looks like a coherence measure. It's not exactly, but looks like a coherence measure.
Yes. I mean, the Kullback-Leibler distance, for example, I think is a coherence measure.
Exactly.
And that comes out as the irreversible entropy production's average. So it depends on what one wants to do. So in this work, we were interested in, okay, so we know that we can extract work from coherences in the optimal way, but what happens if you have a non-optimal situation? How do you include irreversibility? And on the entropy production side, I think that's pretty obvious because you need to find all the trajectories of transfers. Well, okay. Yeah, there's also some stars and asterisks one could add there. But never mind. So, I mean, there's certain trajectories that we use here. which are the eigenstate trajectories. Other trajectories would also give you different definitions of irreversible entropy production. And then likewise for the heat and work, you have to choose what you call it. In either case, I think the story is this: you cannot. It's a bit like you know, when you put something on your tablet or something, like one of those screen savers on your tablet, and you're trying to get the bubbles out. You know what I mean? It's like shifting the bubble somewhere, okay? I don't know how to explain it. It's like bubble shifting, okay? You can shift the bubble somewhere, but it will never go away, if you see what I mean. There's always something. So that's really the point. So the quantum situation is different from the classical situation, and where you push the problem is different for different authors, but we have sort of our framework here, and we can, in our framework, the conclusion is what I showed you before, that the heat.
Okay.
Yeah. Anyway, so yeah, so the quantum version is really different. And the second part of the talk sort of highlights that one more time in a different way. So perhaps that's useful to talk about now. So let me start with this very simple message again. So we have some system, this could be a classical or quantum system, and we do some work and get some heat out to do some sort of trajectory of our system in some time tau. And then one can, all conceptually, one can come up with a probability distribution for the work for all this. And what is known is that if this is a classical system and one does this driving slowly, then it's known that in the slow driving limit, that the system, of course, remains close to the equilibrium state. And what then happens is that the probability distribution of work will become Gaussian. And it will also obey a fluctuation dissipation relation. This is for the work. So this is, it's similar to the standard fluctuation dissipation relation that people know. But here, let me remind you, this is for the work, meaning this is an average over the probability distribution of the work. And this is the dissipated part, which is the difference between W and delta F. So basically, it's this average work, and what the fluctuation dissipation relation says is this is equal to, and this is sigma. Sigma is the width of the distribution. So this is, I mean, the variance, right? You take the probability distribution's variance, and in the classical slow driving limit, these two are equal. And beta, of course, is the inverse temperature. Okay, so this is well known, and the question is, how does it change when you do it quantumly, right? So instead of classical, replace it with slow quantum coherent driving. And the question is, what changes? So you can, for example, think of your classical process as one where the energies of your system may change slowly in time, and then you get this sort of Gaussian distribution here. But in a purely quantum coherent process, you would not change the energy splitting, but you would change the orientation, the coherence of the basis. So the basis at one point in time and at the next point in time is not the same. That is what we call a coherent process. And what I'm saying is that then the distribution will no longer be Gaussian, and this work fluctuation dissipation relation is no longer true. In fact, one finds the quantum work fluctuation dissipation relation to be of this form. So the dissipated work is equal to this stuff that we already looked at, but there's a correction. This Q is not the heat. It's a quantum correction. It was shown by Harry Miller and co-authors here that this is a positive quantity. So this is really an additional term on this side, which means that that this becomes an inequality. If we're just looking at the variance and the mean, then this is now an inequality where the right-hand side is larger than the left side. So let me just say this again. So in fact, this sort of means that basically there's an additional contribution to the variance. So you can think of it as additional quantum uncertainty that comes from the coherence process. So yeah, this is quite remarkable. It's really different from the classical regime. So let me just show you the last slides on this. So what one wants to often do is minimize both the dissipated work, but also the variance, right? It doesn't help to just minimize one of them, because then you have a, you have a huge sigma. So minimizing the middle of your distribution is not going to be so relevant when this is large. So what was found by Harry and Matteo and us was that both the dissipated work as also the variance can be written like metrics. So they're both metrics, and what that means is that one can find optimal protocols, optimal in the sense of minimizing each of those quantities, and these optimal protocols are then the solutions of the geodesic equation. And so classically, one can minimize both. One can minimize the dissipated work and the variance because they are the same and the metrics are the same. So one can minimize both. But obviously, quantumly, you now cannot anymore because they're not the same. So you can either choose to minimize your dissipated work, find the best protocol, minimize this, but then you may pay with a very large variance, or the other way around, you minimize this, but you have quite a large value here. So optimizing a process when you have this inequality is not trivial anymore. And in fact, in general, one can construct a cost function that sort of simultaneously minimizes both. So here's the dissipated work, here's the variance of our distribution. And the beta was there all along. But here now is an alpha, and the alpha tells me how much do I care about this guy and how much do I care about this guy. So obviously, if I set alpha to 0, then we only care about this. And if I set alpha to 1, then we only care about this. And any value in the middle, we care a little bit about each of them, right? So it's a whole cost function set. And then one can explicitly solve for the minimal cost parameter protocol for a given alpha. And then one gets a really funky curve, which is also extremely good to explain. So this is, the term for it is called Pareto front. So what do we see here? We see that, for example, if we plot the dissipated work here and the fluctuations here, then for example, let's look at this yellow curve. This is the curve of optimal protocols for different values of alpha. So for example, if we have alpha equal to 0, this would be the one where we minimize the dissipated work. So this is this end of the curve because this is the minimum dissipation. I can get no lower than this. This is it. Or when alpha is 1, then it would be, we are minimizing this guy. So this is this point, is the end in this direction. And all the other alphas are in the middle. So this is called a Pareto front. It's the simultaneous optimization of both things. And of course, it's the optimum. Optimum means you can do worse than this. You know, think of how do you get from one place to another as quickly as possible. There's an optimal solution. And there's also there are many solutions that are less than optimal, right? And that's what this picture shows here. So the yellow curve is the optimum, and then there are some examples of solutions that are less good than optimum. So they lie on the right side of this, of course, towards higher values of these guys. So what you see here are these Pareto fronts for different temperatures. So the beta is different in these guys. And you see it's quite an interesting and different sort of geometry because classically you have, of course, that both the dissipation and the variance are the same. And so the classical line of optimal FDR is actually this one. So you can always, whenever you find the minimum dissipation, you also find the minimum fluctuation. So they are just this line here for increasing temperature. So you see there's quite a difference between the quantum way of optimizing processes and the classical way of optimizing processes. And that comes because of this difference in the fluctuation dissipation relation. So to summarize, classically, we have this fluctuation dissipation relation and a Gaussian distribution of our work distribution. Quantumly, in a slow process, we have this inequality of the dissipation and the variance, and we have distributions that are non-Gaussian. And one can capture this type of behavior here in this picture here, which tells you the optimum process, which is quite different from the classical optimum process, which is over here. And yeah, with this, I'm now finished. So I'm just going to repeat again the names. So Philip Kammerlander and I did this paper on the optimal work from extraction from coherence. And then this inclusion of irreversibility was something that we did together with Hamid and Alexia. And in the last part of the talk, I talked about this quantum work fluctuation dissipation relation, which was led by Harry Miller and Mateusz Gandhi. And the people who paid the money are those agencies. And I thank you very much for your attention, Lucas.
Oh, thank you very much for the excellent talk. Really nice talk, actually. I learned a lot of things today, but I also have a bunch of doubts.
Yes, okay.
But
sure.
Anyway, before I say something, I would like to give the chance to the audience to make questions. So, is anyone in the Zoom room that wants to make a question to Janet? You can both type on the chat or just open the microphone. Or on YouTube, you can also just type there. I'm looking here. Camille, you open it.
Hi, Camille. Oh, we can't hear you yet, I don't think.
We can't hear you. No.
Oh.
And now, can you hear me?
Yes.
Yes.
Okay. Yeah. So hi. So yeah, my question is following. So if I somehow recap your talk, so in the first part you show how to move from out of equilibrium state with coherence to a state without coherence in a reversible way. And so for that you have a part where you drive, and then a part where you are in contact with the bath, and you do a quasi-static transformation. And the second part is somehow you accelerate that, but not too much.
Yes.
Right. And the question is, I mean, the aim is to have the same, the issue of the first protocol is that, I mean, theoretically, it takes a very long time. You have to be a quasi-statics. And so, I mean, it will depend on the energy gap of your system and so on, but it can take a long time. And so the one aim would be how you can do that still reversibly, or still wasting the least possible work, but doing that faster. And so I mean, as far as I understand, this is the idea of the second part.
Yes.
But yeah, so my question is you said that yeah, you have to, you can do that too fast. Otherwise, I think the approximation that you use are not valid anymore. So the first question is how fast you can go, and secondly, is there any idea or theory or framework to go beyond that? So to go maybe arbitrarily fast. Can we describe? I mean, I know theoretically this is very challenging, but do you know?
Yeah, let me start. Okay, let me start. So firstly, yes, Camille, you make a very good point that may have gotten a bit lost. So the point of doing something slowly is, of course, if you did it infinitely slowly, it could be quasi-static, and then you would not have irreversibility, right? But no one has that much time. So we want to do things faster than infinitely slowly. And that's the whole point. So there's a protocol time tau, and when you include that, then of course you will get irreversibility, and you get, for example, you get even a Gaussian distribution to start with, because quasi-statically this Gaussian could actually shrink to a delta function and all that. So this slow driving limit is for times that are up to order tau, 1 over tau, sorry, 1 over tau. So if you take if you know, this is an approximation. So if you did it not very slowly, really quite fast, in fact, then this expansion that is used to derive the results here will not be valid. So that's the first answer, I think, to your question. And the second one was, how fast can you go? Well, that depends entirely on all the parameters, of course, of everything. But you can go as fast as 1 over tau is really the dominating term, and 1 over tau square is much smaller than that. Then this is valid, this approximation. And then you asked, aren't there also other ways of doing it?
Yeah, so I guess this, I mean, I think so. This theory is like a kind of linear response theory, right?
Yes.
So, is there any way to go beyond that?
Good question. I don't actually know the answer. I guess on the one hand side, yes, because simply one would have to do the calculation to next order up, and then one would get something and so on. It's just a question of how exciting that is, because it's basically perturbation theory to a higher order.
Mm-hmm.
And I think the more interesting direction would be to really look at these things, these shortcuts to adiabaticity. So if the aim is to get from A to B in the fastest time, given a certain amount of resource, then I think this would be your answer. Which isn't the same setup as here. This was simply, we go from A to B with some protocol, and we have time tau to go. And the question is, what is the work and what are the fluctuations, and how to optimize the protocol, sort of the driving speed within the protocol to achieve this transfer.
Okay, so like, yeah, a shortcut to adiabaticity, but in open dynamics, like a shortcut to equilibrium and stuff like that.
Yes. Mm-hmm.
Okay.
Yeah, thank you.
Is anyone else would like to ask a question? Meanwhile, I just check YouTube. Janet, in the last part of your talk, you showed the expressions of the anticipated work and the contribution of the variance coming from the quantum coherency control in terms of some metric structure. Yes, this one. Which metric are you talking about exactly? I mean, is this the metric of the state space, the parameter space?
So what one changes is the Hamiltonian. This is the thing that is being changed in time. And so formally one can expand it in terms of some observables X, right? So for example, think of a, I don't know, position operator, for example, just a single one. And in front of it, you put some lambda, which tells you how you change the magnitude of this Hamiltonian in time. And then what the mathematics gives you is that your dissipated work average is given by such a thing where here you have lambda dot and here you also have lambda dot. So if you have just a single lambda, then forget all the indices, there's just 2 lambda dots. And in the middle you have something, this psi here, and this is sort of the metric part of it now.
Yeah, but that's my question. Which metric are we talking about? I mean, how can I see that this is actually a metric?
Good question. It fulfills all the conditions of a metric. It's not, I haven't got the expression here. I would have to dig up the paper. But basically there is some quite complicated expression for the metric that depends on also on how does the system couple to the environment and so further details of all of that. And all of that is sort of contained in this term. And the reason why this can be optimized is simply because this average dissipated work can be expressed as such a integral over this lambda parameter with this guy in the middle. So then that's how you can find the geodesic equation because of this. I would have to look it up.
Yeah, but this is not the metric of the state space, you know?
No.
Okay.
It's not in state space. It's a sort of it's just a metric in the mathematical sense. You can express, you know, think of like a Brachistogron problem where you say, look, the total time of doing going through some path is this, and you integrate over all the path and all the contributions, and then you want to find the path that gives you the minimum, say, time. And when you do that, you need to integrate over, you know, you need to find out what is the sort of metric in the middle of this integral. I would have to look up again to tell you the details of it. The main point that is really interesting here is that the two metrics are different. So this is the unusual bit.
This is, I mean, related to my question, because when I see expression like this, it is possible to write the dissipated work or the variance or any other quantity in terms of an integral like this, but the metric would be the Fisher information, or actually the entire family of Fisher information, which is the metric in state space. And then that will have infinitely many metrics in the case of mixed states. That's your case. I was just wondering if there is a relation between these metrics and some of the this Fisher information family.
I don't think it is the Fisher information. Again, it has to do with the arisal of these different quantities have to do with the commutation relation of the Hamiltonian spaces at different times. So we have three operators. We have the state at time t, and we have the Hamiltonian at time t, and we have the Hamiltonian at a slightly later time, t plus or something. And all three of them may not commute. If we have a coherent protocol. And so there will be different sort of expectation values or traces over the different combinations of the different order of these three operators. And this is what generates these expressions.
Then I see the metric structure, because these commutators are tangent vectors to this space. That's where it comes from, the metric structure. Okay. But I'm gonna read your paper. Anyway, is the PRL, no? Yeah.
Yeah, that's the PRL.
I see the equations here.
Okay.
Oh, many thanks.
Yes. Okay. Good. Yeah, it's this one here from 2019. Good. Very good question, Lucas.
Yeah, I'm just thinking because I really like geometry and
yes.
And look at the equations of your paper. Now I see the metric structure here. That's really beautiful. Okay, does anyone want to ask some questions? We are 10 minutes past 11 already. So if there are no questions, I would like to thank Janet again for this very beautiful talk. Actually, it's really nice. And thank you very much for having your time and for accepting your invitation here.
Yeah, thanks for listening and have a good day in Brazil.
Have a good evening for you.
Yes, thank you.
Thank you.
Okay.
Bye-bye.
Take care. Bye-bye.
Bye, thanks.
Bye-bye. Ananda. Obrigado, Ananda, pela ajuda. Bom dia para você aí. Bom final de semana.
Prontinho.